All right, now. We had the quiz yesterday. The scores are in PowerSchool. We did pretty well. The class average was around 85 or so, which is pretty good. I don't know. The scores tend to be a little higher average on that quiz maybe than other ones. I'm thinking from year to year when we go over this stuff. But overall, I think that's pretty good. That compares pretty favorably. So, and it was worth more points than the last ones, which is helpful for the grade as well. I will be putting in a homework grade worth about 20 points based on what I've been going around and observing, as I go and check each day and so forth. So that'll be going on there here in the next day or so. We're not going to look at, we still have some people have to take those quizzes, but if you want to come in and see, or at least, just find out kind of what you missed in general, I can talk to you about that a little bit. If you didn't score as well, or whatever, you just want to come, what are things I need, you can come see it. We do have people going to be gone for a number of days with the orchestra and various things that are going on. So we may not hand those back for a little while. Also, I kind of like to hand them back as we get later here into Chapter 2, because we come back, we take a few days to kind of get into the nuts and bolts of what we're learning in Chapter 2, but then we kind of circle back around and bring back the chart concepts and all those things, and so it's kind of a good time to go back and revisit those by going over that quiz at that time, so I kind of like to wait on that. But I do like you to get feedback, so if you really want to see those things you missed, then come in and see me at lunch or after school or something, and we can look at them, okay? So we're going to jump right into Chapter 2 here today, and what's going to happen here is as you look at page 81, it says defining the derivative. And so what we've done in Chapter 1 is we've got kind of a informal definition of the derivative. Its slope, its rate of change. We've estimated a lot of derivatives. We've looked at the tangent line. We've zoomed in, and picked 2 points, done slope calculations, right? We've done that. Now what we want to do is finally get to where we can find the exact slope. How can we do the slope with only 1 point? What's the magic, the secret thing to find the slope at 1 point? And we're going to do that today. All right, so, and begin that process. So at the bottom of page 81, they talk about this Professor X who's driving along. We have some data of their position at the bottom of the page, and we're going to be interested in knowing how fast this Professor X is going right at 2 hours. Okay, so this particular function is going to be d of t is going to be her distance. And we are going to be interested in what is d prime of 2. Okay, what is d prime of 2 equal to? That is our question. Well, just looking at the box on page 81, we could do what? Tell me one way we could find d prime of 2. Okay, now would that be exact? No, that would just be an estimate. So let's go ahead and do that. So, Harry, what 2 points should I use?
I would use the 1.95 and 2.05.
Okay, so my numbers would be 83.54. Somebody get your calculators out and do this calculation for me while I'm writing it. And then 76.54. And then on the bottom, it would be 2.05 minus 1.95. And so that would be approximately how much?
70.
Did you come out exactly 70? Exactly? Okay, so it came out to be 70. Now, we don't know if that's exact really for sure. We don't know if that's the slope right at 2, because really that's the slope between 2 points really close to 2, right? Now, sometimes if you get a really nice curve that is symmetrical, you know, if this is symmetrical around 2, then we may have the exact slope. And I want to show you this diagram right here. Okay, so if I had a curve and I was interested in the slope right here at point A, all right, what we've been doing, and I would like to know that slope right there, all right? So what we've been doing is saying, hey, let's pick 2 points, and normally we've done just what Harry did, is we pick one on each side, because we figure if we pick one on each side, that's a little more accurate, right? The slope's a little higher on the right side on this picture, the slope's a little steeper on the right of point P, and it's a little less steep on the left of point P, so if we pick points in between, we'd get a more accurate representation. So we'll pick 2 points. Now, the notation is really going to be important in this chapter. We're really going to get into the algebra of this. Those of you that like algebra and foiling and working with x's and stuff like that, you'll like this stuff that we'll be doing. Okay? So I picked 2 points, and that gives me a secant line. So remember, every time we do an estimate of a slope, we're picking 2 points. We're not on the black tangent line. We're on the secant line, okay? But if you look at that brown line, it's not too far off of the black line. And we've said, of course, let's let them get a little closer. Now you get right in there, and those two almost look parallel, right? And so, and if this graph had real nice symmetry, like a parabola or something, then maybe this estimate is exactly the same. But it's just by coincidence, really, or not really coincidence, but it's because the curve has some special properties that makes it happen. On most curves, just because you're the equal distance on the left and the right doesn't mean you'll get a parallel. Well, look at this one. We're equal distance on the left and the right of this, and our slope of the brown line is not quite the same. Okay, so most of the time it won't be exact. All right, now notice the notation here. We've called this point A, and we've called this one A plus H and A minus H here. Now the reason we didn't just call those points B and C, right, is why introduce more variables than we have to? We already got point A, so why introduce 2 more? How about if we just introduce one variable called H? And so H is the distance we go this direction, and H is the distance we go that direction. So we'll call this A plus H, and we'll call this A minus H. Okay, now, notice your y values then. You got f of A minus H, and you got, in the green, you got f of A plus H. Right? That makes sense? Right? F of 1, you put in a 1, you get f of 1. Put in 2, you get f of 2. Put in an A plus H, you get f of A plus H. All right. So, what would be our slope equation of that then? Right here on the board, right? We subtract the y's. Well, wouldn't that be f of A plus H minus f of A minus H? In other words, it would be this right down here in the red. If we subtract the y's, we have f of A plus H minus f of A minus H, and then subtract the x's. Now, let's see what you get here. If I subtract my x's, I'd have A plus H minus A minus H. Now, if I distribute the negative, it'd be minus A plus H. The a's would cancel, and I'd end up with 2h. It's really a rise over run, and that makes sense. Since this distance is h here and this distance is h, it makes sense that the run there would be 2h. Okay? Now, so that would be one way to do it. And notice, now here's where the limit is going to come in. And we talked just tiny bits about limit earlier. But what I want to do is let these 2 points get close together. Right? Well, what that means is I want to let h get close to 0. That's the other advantage of using h here instead of calling those points B and C. Right? Then we have to say, well, as C gets close to A, and as B gets close to A. But now what we can do, since we called h this distance in between, we can just let h get littler and littler. So as h gets closer to 0, what that means is these 2 points are getting closer and closer together. Okay, which is something we've been saying since the first day of class. So they get closer and closer. Now the slopes are getting, of course, the brown slopes are getting pretty much the same as the black. Okay? And so we get this. Now, I'm gonna ask you this though. Since we've just been estimating the slopes, we've always said, well, let's pick a point on either side. But is there a reason that we have to pick a point on either side? Why did we pick a point on each side? A little more accurate, right? A little more accurate. But let's go through this now. Okay, I'm going to let A be one of my points. And then I'm going to pick a second point to the right and call it A plus H. Okay? All right, and now I'm going to have a line between those two. Now clearly that one is not very close to the black one as far as slope, right? The brown one was better when I did it. Okay? But keep in mind what we're after here. We're going to let the 2 points get really, really close. So if I let these 2 points get really, really close, won't the green line eventually be just as good as the brown line? You see what I'm saying? If I let H get really, really, really small, if I let those 2 points get really close together, then it doesn't matter if I've picked one on both sides or if I let A be one of the points and then picked one on the right side. And the reason we're going to prefer to do it this way is that our formula is a little easier. Because now look at my two y's. The y's are just, now I just have f of a plus h minus f of a. And then on the bottom, my run here is just h. Right? It'd be a plus h minus a. So it's a simpler formula than the other one was. And since we're going to let the 2 points get infinitely close anyway, let's use the simpler one, okay? So this one in red right here, and let's go ahead and write this down. This is going to be one of, if not the most important definition we write all year long. Okay? The definition of the derivative. Now, it's sometimes called the limit definition of the derivative, but really definition of the derivative is good enough. And what it says is that f prime of a, and we use a because it means at a certain point. Now, tomorrow we'll talk about f prime of x, which means for all x values, and the formula is essentially the same. But for now, we'll do this. Okay, and the formula says f prime of a is equal to, notice, not approximately, but equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. That we will commit to memory. Now, it's not hard. It's only got two parts to it, and they're pretty basic. They're the things we've been saying all along. Let's use some color here. The blue part what is the blue part of the definition? Slope between 2 points, a and a plus h, right? So this is simply slope between 2 points, right? We subtract the y's, so it's f of a plus h minus f of a, and then we subtract the x's, which would be a plus h minus a, which is, of course, just h. And that's just slope between 2 points. It's sometimes called the difference quotient. Okay? The difference quotient. Okay? It's difference because you're subtracting, and then, of course, you're dividing. So, I mean, of course. This is called the difference quotient. So if you ever read or you hear me say the difference quotient, we're talking about subtract the y, subtract the x's, divide them, that's slope between 2 points. And then the red piece, what does the red piece do? let h get infinitely small, right, let h approach 0, which in our example here essentially makes what happen? The 2 points get closer and closer together, or we could say the 2 become 1, basically, right? I mean, that never actually gets there. That's the whole idea of limit, which we'll get into later in this chapter. But the limit as h goes 0, it's getting infinitely close. But common sense would say, essentially, the secant line becomes the tangent line. The 2 points become 1 or get closer and closer together. So the 2 points, let's just say 2 points get closer and closer, ... So the part in red is really the key to it. The part in red is really what takes us from algebra to calculus. Okay? And so I want to make 2 columns here. Average rate of change. I'm probably not going to have room, so I'll probably stack them on top of each other here. But average rate of change is simply f of b minus f of a over b minus a. Right? I mean, well, why that doesn't? Okay. Average rate of change is simply that, slope between 2 points. Now that's one way we could write it, and of course we've just seen another way we could write it. F of a plus h minus f of a all over h. Both of those are the same thing, right? Both of those are just slope calculations between 2 points. Okay? The second one is better than the first one because then we can just let h get closer and closer to 0. Now go back to, ooh. Coming on now? All right. Now, the second one allows us to let h go to 0 and let the 2 points get closer and closer together. The first one would be like this. If we had this point, instead of calling this point a plus h, if we'd have called this b, right? Then this would have been f of b. Now what would we have said as the 2 points get closer and closer together? Instead of h getting close to 0, we'd have said what? As b gets closer to a. So we actually have that one is sometimes used as a definition of a derivative, and I'll write it down here for you. We'll write both of them down. But let's go, okay, let's come back to this. So that's average rate of change. And so what did we call the derivative? What did we call slope at one point? Instantaneous. So instantaneous rate of change, which of course is calculus. See, average rate of change is slope at between 2 points, which you do in Algebra 1. Instantaneous rate of change is slope at 1 point, which takes calculus, and the key is the limit. The only difference here between 1 and 2 is the addition of the limit. So we said if we were using form 1 here, we would want B getting closer to A, right? That would be the 2 points getting close together. Point B is getting close to point A. So we'd say the limit as B approaches A of f of B minus f of A over B minus A. Now I didn't write that one down earlier because that one is a more difficult one to work with, essentially. This one's better. So we'll use form 2 here all the time. But limit as h approaches 0, f of A plus h minus f of A all over h. Okay? So, average rate of change is slope between 2 points. Instantaneous rate of change, which is the derivative. That's what the derivative is. Instantaneous rate of change, slope at 1 point, is the same thing but with a limit in front of it. So there is no magic formula. Just like I told you on the very first day. There's no magic formula to do the slope at 1 point. It's just what we said back then. Take 2 points and let them get infinitely close together. Okay? And this is the notation, and this is what it looks like when you write it. All right, so let's let's look at what an example problem would look like with this. So, so let's take our example up here. On page 84, they say that Professor X has figured out somehow that d of t, her distance, is 10t plus 15t squared. Our emphasis in chapter 2 is going to move from graphs to equations, because in the real world, most of our mathematical stuff is modeled by equations. Okay, so most of the time we do it. You know, the title of our book is Calculus from Graphical, Numerical, and Symbolic Points of View. Well, chapter 1 was all about symbolic. We started off today doing, chapter 1 was all about graphical. We started off today doing numeric. That was that table of data. We did a slope calculation. Okay? Most of what we do in math is symbolic. The symbols. Okay? The equations we're used to seeing. All right, so we want to do d prime of 2. By the definition. Now, sometimes my classes end up calling this the long way, because we do end up learning a shorter way as we work our way through this. Why can't we just do that first? Sorry. Okay, got to get helps with the concept of what's happening. All right. So we want to find d prime of 2 exactly. So we're going to enlist the definition of the derivative. Okay, so in our definition, back here on the last page here, our definition is right here. Now in our definition, instead of f, we have d, and instead of a, we have 2. So everywhere I see an a, I'm going to put a 2, right, for this problem that I'm about to do. All right, so all right, so limit as h approaches 0, right, d of 2 plus h minus d of 2 over h. Next line. Limit as h approaches 0, and you're going to get lazy and you're going to not want to write some of these steps, and you got to be really careful of that. All right? We've had things pretty easy the last week or so. We've been kind of really reinforcing those concepts. Homework hasn't been too long, I don't think. So I hope you enjoyed it. It may change you just a little bit. All right. D of 2 plus h. What's that mean? If I said find d of 3, what would you do? You'd plug a 3 in here for t. If I said find d of 4, you'd put a 4 in here for t. If I said find d of b, you put a b in here for t. And if I said find d of 2 plus h, you'd put a 2 plus h in there for t. Now, we did some of this in some of our earlier problems, and I said the authors kind of foreshadow things you're going to have to do in the future. That was one of them. So right now, for d of 2 plus h, let's call that the red thing. Okay? For the red thing, I'm going to write 10 parentheses 2 plus h plus 15 parentheses 2 plus h squared. See how I did that? That's the red thing. See what I did? Put a 2 plus h in place of t. Minus, now I need d of 2. Oh, let's call it green. Should we get some green in there? All right, let's call that the green thing. It's like Christmas. Okay, what do I get when I put 2 in there?
20.
Now, you could do that in your head, right, if you want to. Now, sometimes it gets a little more difficult than that later on, and so I'm going to go ahead and put, because parentheses are the thing, that subtraction just kills us usually. Whenever you're subtracting a quantity, you know, and we forget to distribute it through, we've got to really be careful of that. But I'm just going to write it out. It'd be 10 times 2, but you can do that part in your head or on your calculator is fine. 15 times 2 squared, you know, but that's got to be in parentheses. Okay? All right, that's the green part. Uh-oh. Work? All right. Ooh. Oh, the green one is. All right. All over H. If you don't stay neat with your work, it's really easy to get lost in some of this stuff. So, limit as H approaches 0. Next line. Now, hopefully, some really nice stuff ends up happening here. We get 20 plus 10H plus, you know, and now how much can we do in our head here? What's 2 plus H quantity squared?
Plus H squared.
4 plus 4H plus H squared. You cannot distribute a squared. You do not distribute squared. It is not 4 plus H squared. You FOIL it, okay? All right, and then I got to take that times 15. Right?
60.
So it'd be 60 plus 60H plus 15H squared. Right? Now, I could have done that in 2 steps, but I prefer to just kind of write it off to the side and then distribute the 15 through. What'd I do?
15H squared.
That's 15H squared. Let's just try that. 15H squared. Thank you. Minus, and what was this? 80. Right? Like I said, hopefully some nice things happen. And I think they do. What happens? If you do it right, some nice things should happen. 20 and 60 minus 80, that cancels. We end up with 70H plus 15H squared all over H. Now, let me stop and make a comment here. The reason we went through all this stuff is because the slope formula doesn't work with 2 points, right? Or with 1 point. Because you subtract the y, subtract the x's, you get 0 divided by 0, right? So I can't let h equal 0, right? Because if h equals 0, the 2 points become 1 point, right? But at some point along the way, we might be able to do that. Now let's look at what we have here. If I put a 0 in for h right now, what happens? I get 0 divided by 0, right? Which is, of course, the problem because our 2 points had become 1. But what could I do right here now on top? What's just begging to be done? Careful with cancel, but what do? You factor out an h, which leaves you 70 plus 15h over h. Now you can cancel an h. Now think about this. Think about what just happened right there. We were saying that if we let h be a 0, that was bad. Well, then we just canceled out the bad. Because there's the 0 divided by 0 right there. Right? So, I'm now left with limit as h approaches 0 of 70 plus 15h. Now we look at that and we say, now let's let h get really close to 0. So now we're saying that, and again, don't get lost in the forest for the trees. Right? In other words, let's step back and see what we're doing. I mean, it's so easy to get lost in all the x's and h's and all that stuff. What were we looking for? We were looking for the slope at 2, right? And we're trying to let h get really close to 0 because that lets the 2 points become 1. What does this number equal as h gets really close to 0? What happens to the 15? It just essentially disappears. If you take 15 times 0.0000001, you know, it's just a really tiny piece. And this becomes 70 plus this tiny piece. And as that tiny piece gets tinier and tinier, what is this answer getting closer and closer to? And of course, that was the answer we had come up with earlier, so it ended up being exact before, but that was just kind of coincidence. That's a really big deal, what we just did right there. We just found the slope at one point. We should pause and just admire what we've accomplished. And I guess we should stop right now. That's enough. That's enough for one day, man. Okay? There you go. And the limit is what made it happen. The limit as h approaches 0, we were actually able to let h be 0 because of some nice algebra that happened for us. Now, that nice algebra won't always happen. We'll have to think about some other things about limits. And we'll do some more of that in Chapter 2. That's called doing finding that derivative by the definition. And you're going to get to practice that a few times in the homework. So I'm sure you're very excited about that. So let's do another one. So you can be ready to do that. So let's take this problem. Let's
John on it.
all right. Now. Okay. All right. Next one. F of x equals x squared plus x. Find f prime of, let's do 3. We don't want to do 2 all the time. You'll think you always do 2. Let's find f prime of 3. This might be one of your homework problems. No, you have one that's a different number in there. So you'll be able to look back at your notes. One of your homework problems is do this, but with a different number other than 3 in here. So again, I want you to have something to look at and follow, but to be able to then do it on your own.
What number?
This is like number, I don't know which one, 6 or 9 or I don't know. All right, so now it won't always say, I mean, if it says use the definition of the derivative or use the limit definition of the derivative, this is what we want to use right here, okay? Right now, that's all we have, okay? This is not estimating, right? This is finding an exact. All right, so tell me what to write. Limit h approaches 0, and I really think if you try to get lazy, and if you try to shortcut too much, I think it really can hurt your understanding of what's going on. I really think it's important to do the function notation first. I think if you get in the habit of doing the, f of a plus h minus f of a, if you really get in the habit of writing f of a plus h minus f of a all over h first, I think that's helpful. Then the second line,
Do we only really have to write
depends how well you want to understand it. Am I going to count off? Probably not. Okay? And then you remember the red thing and the green thing. Okay? Because those are really the parts that we have the most trouble with, is getting that plugged in properly. Okay? But the red thing would be what?
3 plus H quantities.
3 plus h quantity, because our function's different, right? It's not this function anymore, right? We've got a new function.
Quantity squared
So it's 3 plus h quantity squared
plus 3 plus H.
plus that, right? Isn't that the red thing? Because I have to plug the 3 plus h in for all of the x's. So I have to plug 3 plus h there, and I have to plug 3 plus h there. So again, that is the red thing.
Then minus 3
Minus the green thing,
squared.
which would be 3 squared plus 3. All over h. Okay, you guys finish it.
And then we tell you the answer.
Go ahead and finish it. See what you get. Okay? Okay, go ahead and keep going if you're working. Whoops.
Yeah, sounds right.
Okay, foil that out. Okay, foil that out. Make sure you get the minus signs right, things like that. And again, nice things happen. The 12s drop out because, and why is that such a nice thing?
Because in 7 H drops the H.
Yeah, then we could factor out the h. If that hadn't happened, we wouldn't have been able to factor out the h. Okay, so the 12s drop out. We add our 6h and h together to make 7h. We factor out an h. And so as h gets close to 0, this gets close to 7. Now essentially, a lot of you will just look at it and say, well, you just plug a 0 in for h. That's true. But we got to keep in mind that that's only because the h had factored out. If we did, in the beginning, if we plug a 0 in for h, we get 0 divided by 0, which is no good. Okay? But at the end, yes, that's what's happening. Because as h gets close to 0, 7 plus h gets close to 7. And that's what limit means. What does that equal if you could ever get there? Then we say the limit is 7. So what is that? That's a parabola. X squared plus x. I don't know where that is. Vertex, I don't know. Where would the vertex be? Negative b over 2a. What would that be? Negative 1/2. Be the vertex. If you put that in there, it'd be 1/4. Put it down here somewhere. I don't know. Go up here like this. At 3, have a pretty steep slope, wouldn't you? Slope of 7. Kind of makes sense. Kind of makes sense. You could have a pretty steep slope on that parabola at 3. Okay, slope of 7. Because that's what we found. Don't forget what we found. Right? What we just found by that 7 is we found f prime of 3. We found the slope of 3. All right. So we talked about average versus instantaneous rate of change. If you look at the definition at the bottom, page 85, there it is. Okay? The definition of the derivative. It's the way we let 2 points get closer and closer to 1. Your homework then is A lot of it based on that. There still might be some estimate problems where they want you to just pick 2 points and subtract them, you know, and some of that. But there are several problems where to find the derivative, you're going to work this through. Okay, you're going to, what's that?
Do if that H doesn't.
Yeah. I was
Like
just
if-
gonna
Some
say-
other things, but for right now,
Oh.
right now we'll stick with polynomials and the H is going to cancel. But if I had a sine or cosine in there, then all of a sudden some weird things would happen and e to the x, and then we'll have to investigate those and we'll do that. For right now, it's going to work out. Okay? So, your assignment is the top line. Now, let me just make a couple comments as you start through this. Okay? Number one is the first problem we did in class earlier. When we subtracted and did the slope calculation. Write it down. It's in your notes. Whatever. You know what I mean? But that's what it is. Slope calculation. Number 6. Now this is important. Number 6 says find the equation of the tangent line to that curve at the point 280. Now, for number 6, find the equation of the tangent line at the point 280. Well, you got the point. What else do you need? You need the slope of that equation at 2. Do we know what that is?
Yeah.
The derivative of that equation at 2.
70.
Now, if you look at the equation on problem number 6, it's this equation, and you don't have to do this all over again for number 6. We got it. There it is. Okay? So now you can go ahead and do the equation of the tangent line. So you already know that that's 7. Number 7 is this problem, but with a -1. You're doing the slope at -1. It says mimic the computations in example 3. That's what we just did here. Was the computations in example 3. So you're going to mimic this and make sure you can do it. Okay, the rest of the way there are some questions that talk about average rate of change. Some that say instantaneous rate of change. Remember, average rate of change, just do your slope calculation between 2 points. That's what average rate of change is. Instantaneous rate of change would be the slope at that 1 point. Now, in some of them, they give you a graph, and you just do what we learned last chapter. Just estimate the slope. Okay? If it says use the definition of derivative, then you would go through and calculate it the long one. Okay? So understand how that connects. I think some of the ones you're going to do the long way would be like, there's a few of them in there. I can't recognize them right off the top of my head here, but I think you'll notice it when it says it. Now, one last comment I would make would be like number 13. 13 says, estimate f prime by doing the difference quotient with h equals 0.0001. So in that case, if I was going to let h equal 0.0001, then what am I doing? I'm just doing 2 points, right? It's just a slope calculation. I just put a 0.001 in here, and basically what they're saying is, okay, one of your points is 3, one of your points is 3.001, and just do your slope calculation, okay? So the limit as h goes to 0 is finding the exact value. If I give you a really small h, what I'm really saying is, okay, here's 2 points really close, just do your slope. Okay? All right. Go ahead, rest of the time's yours to work. On the top line, yes. Top line. Yes, you gotta do all.
You should take at least 5 numbers.
Like I said, you've had it easy the last week. Now it's time to get to work.
You call that easy?
Most of this would be, I would think, on most of these on this assignment would be no calculator. You know, if thinking about for a quiz, you know, this definition of derivative stuff. Because the calculator will FOIL things out for you. You know, I mean, you can put in 2 plus h, you know, and square it. And it will do that, which is okay, but you really should practice it without it because that's where it'll be on quiz. That's right. 2 8.
Oh yeah.
Just do a slow calculation. Yeah, absolutely. Yeah, average, you know, that's always something that we'll say that a lot this year. Average rate of change, of course, then people think average. They think they want to add stuff up and divide by how many there are, and that's not it at all. When you hear average rate of change, it means slope between 2 points. Average rate of change just means slope between 2 points. Okay? I could stop the recording here.